The track-while scan is a mode of radar operation in which the radar allocates part of its power to tracking the target or targets while part of its power is allocated to scanning. Unlike the straight tracking mode, when the radar directs all its power to tracking the acquired targets, in the TWS mode the radar has a possibility to acquire additional targets as well as providing an overall view of the airspace and helping maintain better situational awareness. Background: early airborne radar systems generally operated purely as tracking systems, with a dedicated radar operator manually tuning the system to locate targets in a relatively narrow field of view in front of the aircraft. The searching area could be moved using a variety of methods, typically phase shifting or lobe switching on lower frequency systems that required large antennas, or by moving the radar dish on microwave frequency radars. Engagements would start with ground controllers guiding the aircraft into the general area of the target via voice commands to the pilot, and once the aircraft got into range its own radar would pick up the target for the final approach when the radar operator would provide voice commands to the pilot. There was no real distinction between seeking out a target and tracking it. Ground-based radars like the -584 Seychelles rupees automated this process early in their evolution. In search mode, the -584 Seychelles rupees rotated its antenna through 360 degrees and any returns were plotted on a plan position indicator. This gave the operators an indication of any targets within its still the 25-mile detection range and the direction relative to the radar van. When one of the returns was considered interesting, the radar was flipped to tracking mode and locked on. From then on it would automatically keep its antenna pointed at the target, feeding out accurate direction, altitude and range information on a bescope display. Operator workload was greatly reduced. Advances in electronics meant it was only a matter of time before automated radars like the -584 Seychelles rupees could be reduced in size and weight enough to fit into an aircraft. These started appearing in the late 1950s and remained common until the 1980s. The introduction of semi-active radar homing missiles made the lock-on concept especially important. These missiles use the launching aircraft's own radar to paint the target with a radar signal. The missile listens for the signal being reflected off the target to home in on. This requires the radar to be locked on in order to provide a steady guidance signal. The drawback is that once the radar is set to tracking a single target, the operator loses information about any other targets. This is the problem that track-while scan is meant to address. In traditional radar systems, the display is purely electrical. Signals from the radar dish are amplified and sent directly to an oscilloscope for display. There is a one-to-one correspondence between blips on the display and a radio signal being received from the antenna. When the antenna is not pointed in a particular direction, the signal from any targets in that direction simply disappear. To improve the operator's ability to read the display, the oscilloscopes typically used a slowly fading phosphor as a crude form of memory. Track-while scan. Track-while scan radars became possible with the introduction of two new technologies: phased array radars and computer memory devices. Phased array antennas became practical with the introduction of tunable high-power coherent radio frequency oscillators in the 1960s. By shifting the phase slightly between a series of antennas, the resulting additive signal can be steered and focused electronically. Much more important to the development of TWS was the development of digital computers and their associated memories, which allowed the radar data to be remembered from scan to scan. TWS radars disconnect the display from the antenna, sending the signals to a computer instead of the display. The computer interprets the signal and develops a track file for anything that would have normally caused a blip. The next time the radar returns to that area, any returns are correlated with the original recording, and the track file is updated or discarded as appropriate. A second system continuously reads the data in the track files from memory and displays this on the radar as a series of annotated icons. Unlike the straight tracking mode, TWS radars have to solve an additional problem of recognizing whether each target discrimination detection defines a new target or belongs to already tracked targets, with the location of targets known even when the radar antenna is not pointed at them. TWS radars can return to the same area of sky on the next scan and beam additional energy toward the target. So in spite of the radar not constantly painting the target as it would in a traditional lock-on, enough energy is sent in that direction to allow a missile to track. A phased array antenna helps here, by allowing the signal to be focused on the target when the antenna is in that direction, without it having to be pointed directly at the target. This means that the target can be painted for a longer period of time, whenever the antenna is in the same general direction. Advanced phased array radars make this even easier, allowing a signal to be continually directed at the target. The original tracking radar system was the semi-automatic ground environment system developed for the U.S. Air Force. SAGE required enormous computers to develop and maintain tracks for up to dozens of aircraft. Early airborne TWS radar typically only tracked a single target while scanning. The original TWS airborne set was the Hughes aircraft and ASG-18 of the XF-108 Rapier, which could track a single target. The Westinghouse and APQ-81 for the F-60 Missileer was more advanced, tracking up to 8 targets, but required its own operator. It was not until the introduction of digital computers, and especially microprocessors, that TWS in airborne applications became practical. Development of TWS generally followed the development of the microprocessors that eventually powered them. The Ant-9 Aruba and Florence of the F-14 Tomcat used an Intel 8080 and could track 24 targets.